I can send a command from my computer to this turntable. Check this out. I'm going to click send command here, and it lifts up. How neat is that? Hello everyone, it's time for another Statomatic Science video, and today I'd like to take a look at my automatic turntable. And if you're unfamiliar with this one, this project encompasses my quest to build a high-quality, fully automatic turntable from scratch, which I'm calling the Statomatic STM01. In past episodes, I nailed down the requirements for this turntable, fleshed out parts of the electronics, and finished the tone arm. So at this point, it's playing records using another turntable, and we can use a button to lift the tone arm up and gently set it down. And if you'd like to see a deep dive of how I got to this point, you should check out some of my earlier videos. I go into a lot of detail of what I did for each step. Now we have the turntable lifting the tone arm up and down, but I really want to dive in there and do the azimuth movement so I can have it moving left and right as well. But the problem is there's some other things that I want to implement first before we get to that point. And those things are going to make troubleshooting a lot easier going forward. And this includes error statuses, statuses in general, and commands going into the turntable. If I can implement these three things today, the azimuth movement is going to be a breeze, or at least a lot less difficult than it would be otherwise. It's still going to be pretty difficult, but that's for future me to worry about. A very important part of this project is the group of status LEDs. These are just going to be lights on the turntable that tell the user what's going on. Like for example, one of these squares would be illuminated, telling the user which speed is selected. And though there are a lot of pins on the Teensy 4.1, I'm already planning to use most of them, and I'd like to have a lot of status LEDs. To accommodate this, I've decided to use the MCP23017 shift register to house all of my output statuses. So this chip will be responsible for illuminating the selected speed, selected size, the movement status, and some internal functionality. And the best part is it only costs 2 microcontroller pins to use, so I'm saving 14 pins using this thing. The code that I wrote to use this shift register is pretty simple because we can just use the Arduino wire library to handle the I2C data transmission. I prototyped this out on the breadboard using lots of fun-colored LEDs, and my implementation appears to work as expected. So I followed that up by setting the appropriate LED when the pause command is active. Now the only thing the breadboard needed was a way to propagate this value up to the user interface. So I added some connectors to facilitate this. I then attached some ribbon cables to the female ends of the connectors, soldered up some LEDs to the other side, and gave everything a quick test. And yeah, that's looking good. These cables will definitely work for our status LEDs. I also wanted the buttons themselves to be a little bit easier to use because the small ones on the breadboard move around all the time, so I gave those the same treatment as the LEDs. I wired up a connector on one end and then 4 Cherry MX Blue key switches on the other. These have a satisfying click when they're pressed, so I love using these in projects whenever the opportunity presents itself. So we have output statuses that roughly tell us what the turntable's thinking. So what about error handling? What do I even mean by that? Let's start with a hypothetical scenario. Say you're going to use your turntable and you trigger the automatic homing routine, but while the tone arm is moving, it gets stuck, either by an obstruction or maybe the hardware started to fail. On a fully mechanical turntable, if it gets stuck, well, it just tries to keep going and is none the wiser that it's not carrying out the movement it intends to. This is the same story for every turntable or record player with a fully mechanical automatic mechanism. Some of them are engineered such that when the unexpected happens, it just keeps going and nothing gets damaged. Some turntables will get themselves tied in knots and rip apart plastic gears, and some of them just get stuck and wear out the idler wheel, belt, or direct drive motor. And if you've ever repaired these machines, you've probably seen that the worst case scenario is when the lift itself fails to lift the tone arm up, and it drags the stylus horizontally across the record. So now you've ruined your record and your stylus. Hopefully it wasn't a moving coil cartridge. Anyway, these scenarios are a significant disadvantage to a fully mechanical automatic mechanism. But on a digitally controlled system, like the one I'm building here, we can incorporate potentiometers, encoders, and limit switches to our advantage, and halt movement when we notice something's gone awry. For instance, we have this lift mechanism that can move the tone arm up or down. But how do we know it's actually moved up and is safe to move horizontally now? That is what the slide potentiometer is for. This slide potentiometer is measuring the position of the lift as the movement executes, and the movement only ever completes when it's reached its target value. Now that said, the important question is, what if it gets stuck? Does it just keep trying to move the lift indefinitely because it can't actually reach its target? And the answer to that is, yeah. If I were to put a lock on the tone arm and try to use the lift command, it just keeps going and going and going. It'll probably hurt itself if I let it go for too long. This is where we can really use this encoder to our advantage. I wrote a simple algorithm here such that if the motor makes so many steps and the encoder hasn't incremented, then it stops moving and throws an error. Here's an example of that working with the tone arm locked as it was before. Now, instead of indefinitely moving and hurting itself, it recognized that something's gone awry and set itself in an error state. The error state just looks like the power LED blinking, and then an error code is shown using the size and speed LEDs, which corresponds in binary to the errors that I set in this enumeration. This way, if the turntable ever encounters one of these errors, we can cross-reference this enumeration to see exactly what happened. So with this system, I'm pretty confident that not only can we send these commands, but we can also verify that they successfully completed before moving on to the next step or the next command. Now this next part is the part I am most excited about, and that's external commands. What I mean by external commands is that I want to give this turntable the ability to receive commands beyond the buttons I'm making available on the main user interface. The end goal is for these commands to be sent via external modules like a record changer, a second tone arm, and so on, making this turntable essentially modular. So you could use the basic STM01 turntable as just a standard standalone turntable, or you could attach different modules to it to expand it to be a record changer, essentially a jukebox. The possibilities are truly endless, at least in my opinion. For the STM01, I'm planning to have 5 external module connectors. Technically 6 if you include the USB, which we'll be using for testing. In a previous episode, we went over this really simple software flow diagram where we read our serial input, read command buttons, and then execute a command. Expanding on that read serial input step, now we're going to separate that into 6 steps, one for each serial port starting at 5 and then ending at USB. We can break down each of these serial steps by first checking if there's any data to be read. If yes, we check for a data start key. If yes, we determine if we're executing a command, requesting data, or changing a setting, and then repeat this cycle for the next serial port. Now going back to that data start key, this is something that I added at the beginning of the command just to make sure that the device that is sending the command is compatible with the STM01 turntable, because I plan to make other turntables down the road, so if you plug a module that's not compatible with a different turntable, I want to make sure that command is getting ignored. That said, each command going to the turntable will have 3 distinct sections: the key, the command, and the command data. The key will occupy the first 8 bits of data, the command will occupy the next 8 bits of data, and remaining bits will be occupied by any command data, if applicable. Alright, so we have a solid plan, so let's go write the code. Hello, I'm over here now. So I have the turntable hooked up over here, and I have the serial monitor doing its thing. And in the code, just like in the block diagram, I am checking if there's data available, checking the command key, which is in constants here. It's just the letter M in ASCII. And then we should see received command if we get the command key. And then if the next character is a valid command, which I have in this external command enumeration, pause or unpause is just 1, which is just some strange ASCII character that I'm not really sure of, but I've just been copying and pasting it using this ASCII converter I found online. So it's pretty straightforward and it should just work. So we're going to give it a shot. So I think I just need to type in the letter M. Nothing happened. Oh, right. So I'm checking if it's greater than 1 character. So there should be 1 character in the buffer right now. So if I send another character here, there we go. So we received a command, so we made it in this block. I sent 2 M's, so one of them was the key, and the second one doesn't match up with anything in the switch statement, so we'll try executing this command. We'll copy our ASCII character in our clipboard here. We'll type the letter M, and we'll submit that, and we should see something. There we go, look at that. So the pause command got executed as if the user pressed a button on the turntable, but the command was sent remotely from my computer, so we'll do that again for good measure. We'll type the letter M here. You can't see it in the terminal, but I am typing the letter M. M, and Control V. That is awesome. So we'll do it again. Yeah, look at that. That's exciting. We're officially sending it commands now, so that means communication between the modules is totally possible with this. Not that I thought it wasn't before, but now it reinforces that this is in fact something that we can do. So I'm going to spend some more time writing some other commands and we'll see what I come up with. Hello again, it's me. I've spent some more time with these commands and I figured some stuff out, so let's go check that out. So to make all of this easier, I wrote a Windows application in C#, and that will let us send data to and receive data from the turntable and make things a lot easier than just typing raw commands into the terminal. Now going over the software I wrote, we can see a list of devices connected to the computer, COM5 and COM9. I'm pretty sure COM5 is like my phone or something, and COM9 is the turntable. If I try to connect to COM5, it's going to give us an error. Well, that's not supposed to show that. Interesting. So that was not the error that I was expecting to see. That is a bug. I'll need to fix that later. But if we connect to COM9, it'll connect to COM9 port. It'll test the connection, which is successful. Great. We can test the connection several more times if we want to. All this does is it sends a connection test command to the turntable, and then the turntable sends back a success code. And then we make sure that that success code equals what we expect it to. And then once we're connected, we can just go through all the commands that I have implemented so far. So the only action command that I have is pause or unpause. So if I click send here, then we see the turntable lifts up. And if I press it again, it'll set down. Now something that's pretty cool is that when you send the command from the computer, so if I press send command here, that is exactly the same as pressing the pause or unpause button on the turntable. So even though the command's getting executed from two completely different spots, it's executing the exact same code, and therefore we have the same error checks no matter where we're executing that from. And you probably noticed every command that I send in this program is logged, and this is so that if I do some strange combination of commands that causes an error, I can trace it back to what happened. Now to do a demonstration of that, let me lock the tone arm here quickly. All right, we're locked, and we'll try to send the pause command. And that fails as expected. We can see the power LED flashing that indicates it's failed. We can go over here to get value and we can get the current command. It says it's in an error state. That's good. We can check the error code too now. So if I click send command, this is going to tell me why it's failed. And there we go. The error code is the lift failed stalled moving up. So that's awesome. So what this tells us is when the turntable fails for any reason, we can get detailed output for exactly why it failed and what went wrong in the routine. And if the commands were sent from the computer, we can get a log tracing back to how it got to that point. Now for this turntable in its final state, obviously it's not going to be hooked up to a computer all the time. Ideally by that point it's going to be stable enough that it can function on its own. But in the early testing stages, this logging is going to be highly important. Now I'm not going to go over all these commands, but there's a few more in here that can just pull data from the turntable. Horizontal encoder position, I don't have that hooked up yet, so if I try to send that, it's just going to say the turntable didn't respond. But we can get the current uptime, so if we send that, I've apparently had it running for over a day. Probably shouldn't do that, but it works, so I did. So another exciting one is the home status, and I think this demonstrates pretty well that we can look at the turntable statuses from really any module that's connected to it. So if I click send command here, we can see that it's currently homed. Now if I were to lift the tone arm up and send that command again, we see it's not homed. And like I said before, what this demonstrates is that a module that's connected to the turntable can accurately read the turntable's state at any given time and know exactly what's going on. So if you only want to run commands under certain scenarios, you can check the turntable statuses to make sure those scenarios are fulfilled. Now going back to this uptime command, I think this is a particularly exciting one, and I'll explain why. So by itself, all this does is tell us how long the turntable's been on. But what's important about this is it tells us that we can maintain statistics in the turntable and retrieve those at any time. Like, for example, how many hours do you have on your stylus? How many records have you played? How many 7-inch records have you played? You can get all of those statistics from the turntable. Granted, I'm not logging any of them yet because I don't have any of that functionality hooked up, but the possibility is there. But anyway, to sum it all up, I think this is really exciting because this shows that we can read exactly what state the turntable's in and we can read statistics from it. So all those modules that I talked about before are going to be possible with this logic. And the possibilities are truly endless, or at least limited to the ROM and RAM that the TNZ 4.1 has. But realistically, I don't think we're going to reach that limit. At least I hope not. And so we've closed another chapter of the Statomatic STM01's design journey. Though I didn't do a lot of physical design work in this episode, the shift register, error codes, external commands, and this testing software are all huge parts of this design. And to be honest, that makes this turntable massively over-engineered, but that's exactly how I want it to be, so I'm going to keep doing that. And I gotta say, I'm really excited about these external commands. I knew this was going to be exciting, but when I saw it running on the software, it's different when you see it happening versus when you just think about this idea. So I'm excited to make a tone arm or a record changer, whatever else I think of, I don't know. There's a lot of possibilities. There's a document that I have on GitHub that you can look at the ideas that I have so far. Those are eventually going to make their way into videos too, but for now we have to design the Statomatic STM01 turntable first. Gotta have something to receive the commands after all. But I digress. I am a very long way away from achieving that, so we're going to have to do all the other stuff first. And speaking of that other stuff, in the next episode, I'm thinking I'm going to take a little bit of a break from the technical aspect of the project and do a little bit more with the visuals. So maybe I'll be able to turn this 2D plan into a real user interface, or at least a partial user interface, since I don't have the turntable part finished yet. Will it look nice? I don't know, but it's not going to stop me from trying though. So maybe we can make it look a little bit nicer. And if that journey sounds interesting to you, maybe consider subscribing and you can join me together and see where this project goes. Anyway, that's all I have for you today. Thank you so much for watching, and I really appreciate you watching to the end here, and I look forward to seeing you in the next episode.